This is the Space Launch System, the most powerful rocket NASA has ever flown. It takes shape inside a New Orleans factory big enough to hold 31 football fields, where a rotating pin plunges into an aluminum seam and spins almost too fast to follow. It never melts the metal. What rises here takes more than a year to build, for what SpaceX stacks in days, and cost $4.1 billion a single flight. Every decision in this building looks insane, until you understand the one thing this rocket is built to guarantee. Behind that pin, two curved aluminum panels fuse into one continuous joint, a zipper made of metal, no seam left to find. A technician checks the finished weld. He can't find where one panel ends and the other begins. Neither can the X-ray. And it's not luck, it's the process. That joint is stronger than the surrounding metal, with zero voids and nothing hiding inside that could ever grow into a crack. The factory hums around him. Saturn V first stages got built on this exact floor in the 1960s, and space shuttle fuel tanks after that. Now it builds the core stage of NASA's Space Launch System, SLS, one obsessive weld at a time. That spinning pin is doing something called friction stir welding, and it isn't welding the way a shipyard means it. Nothing melts, nothing gets added. There isn't even a flame. Instead, the machine essentially forges two panels into one continuous piece of metal. The best way to picture it is clay. Press two colors together and twist until the seam disappears completely. The vertical assembly center does the twisting. A 170-foot robotic tool NASA calls the largest of its kind on Earth. A single weld can run for hours, clamps holding everything rigid. Any movement during the stir means a flaw locked inside the joint forever. The machine never rushes. The metal is what sets the pace, and it doesn't negotiate. The biggest thing it builds is the liquid hydrogen tank, and this is where the scale gets stupid. The single tank runs 130 feet of welded barrel sections and domes, and every seam stirred shut by that spinning pin. Right now, it's holding nothing but air, and stays that way until Florida. Why go through all this? Regular welding, the melt it and fuse it kind that builds ships and skyscrapers, leaves microscopic gas pockets behind. A bridge can live with those pockets forever. This machine can't. One void in one weld under 8.8 million pounds of thrust, and the tank wall lets go, and the rocket stops existing. Every weld also lives a double life. On the ground, the tank walls hold propellant cold enough to freeze steel brittle. In flight, those same walls carry the weight of everything stacked on top of them. The tank isn't inside the rocket. The tank is the rocket. Spin the pin too fast and the softened metal tears. Travel too slow and the heat builds until the joint weakens. Crews track temperature, force, and speed across every inch of seam. And the process that was supposed to guarantee perfection nearly broke the program. No one had ever friction stir welded tank walls this thick, so engineers had to figure out the recipe from scratch. What they didn't know yet was how long the recipe would fight them. It didn't go well. Tooling got redesigned, then redesigned again. The learning curve swallowed more than 2 years. By 2019, federal auditors found Boeing, the company that built it, more than $1 billion over budget on this one stage alone. That overrun stung no one in the boardroom. NASA builds this rocket on a cost-plus contract. The government covers the bills, whatever they are, and even adds a guaranteed profit on top. When the welding runs long, the taxpayer covers it. Redesign the tooling 3 times, and that bill lands on the taxpayer too, with profit attached. There's no financial penalty for being slow, just a guaranteed check. But the welding is the easy part. The hard part is bolting 5 of these welded monsters into one rocket stage so that the margin of error is thinner than the paint. Across the floor, crews crawl through 5 huge structures fresh off the welding tool. 2 giant propellant tanks, the rings that connect them, a forward skirt, and the engine section. Welding only makes empty shells. They clean each tank's interior, prime it with a robotic arm, then thread in the wiring, the fuel lines, and the flight computers. Miles of cable run through spaces a person can barely crawl into. By the time a piece is ready to join the stack, it's less a tank and more a building with utilities. Then they bolt it all together, one mating ring at a time. Technicians machine every ring to 1/1000th of an inch before anything touches anything. That's a sheet of printer paper sliced into 4, held around a ring 27 feet across on a part that weighs as much as a house. And the standard isn't vanity. A ring that's off by the thickness of a fingernail means the thrust line bends in flight. And you don't get to fix that at Mach 23. The forward assembly, the rocket's top third, meets the hydrogen tank in a slow-motion docking that takes days. Technicians drive 360 precision bolts around the mating ring, each one torqued in a programmed sequence so the strain spreads evenly. Skip a number in the sequence and you warp the ring. Torque too close and vibration works the joint apart in flight. Torque too tight, and the ring carries stress it was never built to hold. Lasers sweep the roundness of each barrel and the flatness of every mating surface, then check that the entire stack lines up perfectly straight. One measurement out of spec and the structure goes back, not for repair, for rework. At these tolerances, you can't patch a problem. You either fix the root cause, or you take the whole thing apart and start over. The finished stage stands at 212 feet tall, the largest ever flown. It weighs 188,000 pounds dry, lighter than an empty 747. Why so light? Because almost all of it is empty tank. And what those tanks are for, you'll see at the launch pad. It won't go smoothly. Down at the engine section, a crane swings a nozzle taller than the technicians guiding it. They walk it into position by hand signal and torque it home. The first of 4. No ceremony and no nameplate, just another line on the checklist. Except the hardware swinging onto this stage has already been to space. 3 of the 4 engines bolting on this week are shuttle veterans. 22 missions between them, and the most traveled of them flew 15 times, including the very fast shuttle flight in 2011. These are RS-25s, the most tested large rocket engines in history, 7,700 pounds apiece, burning liquid hydrogen at 6,000 degrees through a fuel pump spinning at 37,000 RPM, fast enough to drain a backyard swimming pool in 25 seconds, built to fly 55 times each. These aren't museum pieces getting a victory lap. They're the most proven engines America has ever flown. A loose fitting here doesn't get discovered later. Later is 8 minutes of maximum thrust with 4 people riding on top. So crews check every plug and fitting, fuel, hydraulics, data, then check it all again. And after this mission, NASA drops all 4 engines into the Pacific, on purpose. The Pacific already holds 4 from Artemis I. Congress wrote that fate into law. Reuse the shuttle's hardware, keep the factories and the jobs open. The logic held right up until you trace the flight path. The space shuttle came home. This rocket doesn't. The core stage drops away while it's still aimed at the moon, then falls into the ocean with no runway or recovery ship waiting, no second act. Engineers ran the numbers. Recovering the engines would cost more than building new ones. So 50 years of engine development flies once, then sinks. The world's most expensive skipping stones. The engine and booster contracts tell the rest of the story. Planned at $7 billion and now worth more than $13 billion and counting. Cost plus contracting, remember, which leaves a 212-foot rocket stage in New Orleans and a launch pad 900 miles away in Florida. Too tall for every bridge in America, too heavy for any aircraft, and too wide for any rail car. There's exactly one way to move it. The finished core stage rolls out of the factory in July 2024, horizontal and sealed inside a climate-controlled cover. Crews chain it to the deck of a barge called Pegasus. Tugboats ease it into the water. Most cargo ships make this run in 2 days. Pegasus takes the better part of a week. Pegasus is a shuttle-era veteran that hauled the big orange fuel tanks out of this same factory when the new stage outgrew it. NASA stretched the hull by 50 feet. It has no engines of its own. Tugs push it every mile. It's not fast and it's not pretty. It's just gentle. The route runs down the Intercoastal Waterway, into the Gulf, around the southern tip of Florida, and north to the Tern Basin, Kennedy's private harbor. It hugs sheltered water start to finish. Open ocean swells flex thin-walled tanks aligned to thousandths of an inch. Speed creates vibration, and vibration undoes weeks of laser measurement. Inside the cover, climate systems hold the air steady. Not because the stage minds the weather, but because aluminum moves. Too hot and it swells out of tolerance. Too cold and it contracts past the other edge. So the rocket rides in air conditioning. $500 million in hardware cruising at jogging speed past guys fishing for redfish. Sensors on the deck log everything: temperature, humidity, vibration. If any number drifts out of line, inspectors at Kennedy will know exactly when and where it happened. The stage that arrives has to be the same stage that left, and the paperwork has to prove it. That logbook follows the rocket all the way to the pad, and the pace isn't a limitation, it's the point. Slow is the whole design philosophy. Floating. At Kennedy, cranes lift the stage off the deck and roll it into a building so big it makes its own weather. And then the slowest part of the whole program begins. A door 456 feet tall starts to open, and it keeps opening for the next 45 minutes. The core stage rolls through it into a single room with clouds near the ceiling, real ones. On humid days, Florida air drifts up into all that empty space and turns back into water. It's rained, indoors, in this building. This is the Vehicle Assembly Building, 525 feet tall, one of the largest buildings by volume on Earth, built to stack 4 Saturn V's at once. Workers cross the floor on bicycles. Under that occasional indoor sky, the tallest crewed rocket in American history starts going vertical. It doesn't start with the core stage, though. Nothing goes vertical until the boosters do. The core has nowhere to bolt in without them. The first segment goes up on November 20th, 2024. A crane operator threads it down toward the mobile launcher, the steel platform that this rocket rides to the pad and launches from. The segment is 150 tons of solid fuel and steel, swinging through a high bay on a cable with inches of clearance on every side. There's no margin for a bad day here. Solid fuel doesn't rain. Once it's cast into a segment, it stays there until it burns. Segment by segment, 2 towers of white steel climb to 177 feet each. Work runs through the winter holidays and into February. Booster stacking alone takes 3 months, and the boosters are the fast part. The big one comes March 23, 2025. This is the piece from New Orleans, welded, shipped at jogging speed, measured to the thousandth of an inch. And now it rises off the floor and swings between the 2 boosters. Crews bolt it home, and the rocket finally has a backbone. April adds the adapter ring. May, the upper stage that'll push the crew toward the moon. Late May brings the moment the rocket stops being parts. Crews light up the core stage and boosters together for the first time, and thousands of sensors wake up and start reporting. Engine controllers responding. Booster systems checking in. The stack is alive, and now all of it has to prove it. Orion arrives in October. Its escape tower, built to yank the capsule clear of a failing rocket in seconds, rides on top. 11 months of crane lifts sounds glacial until you realize each lift swings an irreplaceable part over an irreplaceable rocket. The finished stack tops out at 322 feet, taller than the Statue of Liberty. There's a record buried in the engineering paperwork that no one advertised. At 239.5 feet, the core stage plus its adapter stands 7 feet taller than SpaceX's Super Heavy booster. NASA quietly owns the tallest rocket stage ever assembled, and no one held a press conference. So why does NASA take a year to stack what SpaceX stacks in days? Watch the crews between the crane lifts. They verify every electrical connection, then verify it again after the next lift changes the picture around it. They pressure test the propellant lines, leak check them, and test them once more. This isn't bureaucracy, it's doctrine. One unverified connector on a crewed rocket means an abort on the pad at best, and you don't want to learn which connector it was at T-10. NASA calls it test like you fly. Every system has to earn its place in the exact configuration it'll see on launch day. The same wiring, plumbing, and software load it'll fly with. That's the year right there, not slowness. Verification stacked upon verification. Proof doesn't last long in this building. SpaceX blows up prototypes on the pad and calls it data. That's a legitimate engineering philosophy when the rocket's empty. NASA can't use it here because this one carries people, 4 of them. Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. The first humans headed toward the moon since 1972. All of it the slow welds, the retests, the billions. It comes down to one requirement. Those 4 come home. The $4.1 billion isn't buying speed. It's buying a failure rate of 0. Fully stacked, it's 322 feet of rocket that's never moved an inch. The launch pad sits 4.2 miles away. Rollout night arrives on January 18, 2026. A machine the size of a baseball infield slides under the mobile launcher and lifts the entire stack onto its back. The treads bite, and the whole assembly grinds forward. 8 tank-style tread sets, links a ton apiece. That's Crawler Transporter 2 doing the carrying. 6.6 million pounds of machine before you add a single pound of rocket. 12 hours later, it's still moving. Top speed is 1 mile per hour. A laser-guided leveling system holds the stack vertical the entire way. Hydraulic jacks at each corner, adjusting non-stop as the ground rises toward the pad. Tilt past tolerance and everything stops until the jacks catch up. From the cab, a driver steers all of it at a pace slower than a casual walk. Look down at what those treads are crushing. It isn't asphalt and it isn't concrete down there. It's river rock. Rock crushes quietly instead of sparking. And 1 spark under a rocket is 1 spark too many. This road isn't really a road. It's a safety system you can drive on. These crawlers have been making this exact trip since 1965. Apollo first, then 3 decades of shuttles, now this. Crawler Transporter 2 is older than most of the engineers riding it. In 60 years, it's never tipped a rocket. The final stretch is the worst, a 5% grade up the ramp to pad 39B. The jacks tilt the platform against the slope so the rocket never leans. Fraction of a degree by fraction of a degree. Up top, the crawler lowers the launcher onto its pedestals and backs away. The rocket has arrived. Now it has to prove it can drink. On February 2nd, 2026, pumps start driving propellant tanks that have sat bone dry since New Orleans. 733,000 gallons of liquid hydrogen and liquid oxygen at minus 420 degrees Fahrenheit. Welcome to the wet dress rehearsal. And the name undersells it. This is a complete launch day countdown minus the ignition. The fill rate is everything. Pump too fast and thermal shock hammers the seals. Pump too slow and the countdown stalls past its window. Every console read nominal. What the launch team couldn't see yet was that hydrogen had already found its way out. Then, 55% of the way to the fill, hydrogen finds a gap it always finds. A leak opens at the umbilical plate where the fuel line meets the base of the core stage, the same connection that plagued Artemis I back in 2022. Engineers stop the flow, let the hardware warm so the seals reset, then coax the tanks the rest of the way full. The rehearsal limps to the finish. The February launch window doesn't survive it. Liquid hydrogen earns its reputation. It's the smallest molecule in the universe, and it slips through gaps nothing else can find. Shuttle crews fought this exact enemy for 30 years. The machine built on perfect seals just met one substance that hunts imperfect ones. And hydrogen wasn't finished. February 21, overnight. A different gas fails in a different stage. Helium stops flowing to the upper stage. And helium isn't optional. It keeps the tanks pressurized and flushes the oxygen lines clean. Without it, nothing flies. Engineers can't get at the broken part on the pad. The entire stack crawls back to the vehicle assembly building, and the March windows fall with it. Rolling back takes just as long as rolling out, 12 more hours in the wrong direction. The astronauts, quarantined since January, walk back out into the world. They'll quarantine again for March, then again in April. Somewhere in Houston, 4 of the most patient people alive keep repacking the same bags. Here's what that rollback actually was: the system working. The wet dress rehearsal exists to drag flaws out into the open while the crew stands safely on the ground, not strapped on top at T0. It found 2, caught on the ground. A leak is a schedule problem. At altitude, it's something far worse. Engineers traced the helium fault to its root cause, designed a fix, tested it, and proved it safe to fly. March 20, the crawler delivers the stack back to the pad, ahead of schedule. April 1st, the window opens at 6:24 p.m. The rocket that's scrubbed twice gets 1 clean shot. The weather holds. 6:35 p.m. The countdown hits 0 on the first attempt. The twin boosters light. 7.2 million pounds of thrust in 2 seconds, more than 80% of everything this rocket has. And once they're lit, nothing on Earth shuts them off. There's no throttle and no off switch. You're going to the moon or you're going swimming. Then the 4 veterans join at full power, 416,300 pounds each, 8.8 million combined, the most thrust ever put under a crew. A column of fire climbs out of Florida, visible from Orlando. 3 miles away, the sound arrives seconds late and lands as a crackle you feel in your chest. 2 minutes in, the boosters burn out and punch away on separation motors. They're part of the job done. Inside the capsule, the ride smooths out. The 4 RS-25s keep pushing alone, throttling against the thinning air as the rocket leans downrange and accelerates past 17,000 miles per hour. 8.5 minutes of full throttle, and the veterans finish their last job. The welds hold. The 360 bolt joints hold. The core stage lets go and arcs toward the Pacific. The splash NASA priced in from the beginning. Orion sails on with 4 people aboard. They ride the same shake and press that shuttle astronauts described for 30 years. April 6, 1:57 p.m. The capsule, the crew named it Integrity, crosses 248,655 miles from Earth and keeps climbing. That number stood for 56 years. Apollo 13 set it in 1970, and no human had been farther since. 56 years is a long time for a record to stand. This one outlived the program that set it. Integrity doesn't stop until 252,756 miles, the farthest from home any humans ever been. The crew skims 4,070 miles above the far side of the moon at 3,139 miles per hour, looking down at ground no humans ever seen with their own eyes. Wiseman, Glover, Koch, and Hansen. 4 people riding an engine design that first flew in 1981, when the youngest of them was only 2 years old. The trip home ends at 25,000 miles per hour. Orion hits the atmosphere faster than any crewed capsule since Apollo, and its heat shield carves through air compressed into plasma at about 5,000 degrees Fahrenheit. 2 drogue chutes drag the capsule down to roughly 300 miles per hour. 3 pilot chutes pull out the mains. The mains slow it to 17. April 10th, 8:07 p.m. 3 parachutes bloom over the Pacific, and a capsule carrying 4 living astronauts slaps the water off San Diego. Recovery teams aboard the USS John P. Murtha move in to collect them. And back in New Orleans, on a factory floor the size of 31 football fields, a spinning pin's already buried in the seams of the next core stage. If you enjoyed this video, then watch how the ugliest airplane in the world carries other NASA pet projects. Bye for now.